I will get that to you on Thursday. Come hell or high water. So we've talked a little bit about evaluation of different things, and right now we're in the middle of talking about polynomial interpolation. Later on this semester, we'll talk about kind of piecewise interpolation, if you will. But a lot of it's about evaluating polynomials. And we talk about polynomial approximations and so forth, so that's why your first major assignment is about evaluation of polynomials, and in particular, how to do it more efficiently than just doing multiple powers of things. So if you think about the way a polynomial is originally written, the higher the x goes, the higher the multiplications you have to do, and then you go to the next term, you have to do a whole bunch of multiplications there, and so on down the line. This assignment hopefully will lead you through doing things with Horner's algorithm. If you've done synthetic division before in an algebra class, you've done Horner's algorithm. It's the same thing. Okay. But the idea is to not have to do a bunch of multiplications all at once. It's about doing a multiply and an add, and a multiply and an add, and trying to cut down on the amount of multiplications. So that's the point of the assignment. Okay. Also, which you probably have not seen before, which is another reason why I have this assignment, is that you can actually do continued synthetic division, if you will, to be able to evaluate derivatives of polynomials in a quick fashion without actually having to differentiate. So that's what the end of the major assignment is. Feel free to ask me questions about it. Okay. And yes, I know you can find a lot of the stuff on the internet. I don't want you to just copy down what you see on the internet, okay? Which actually work on it. All right. Struggle through it, see what's going on, see the individual pieces and those kinds of things. So, but again, you're more than welcome to come ask me questions. I'm happy to answer questions. What I do not want you to do is just type it into an AI machine and have it just generate the answers. So please don't do that. All right. All right. So let's pick. Are there questions before we go on? You have homework due on Thursday, right? Moved it to Thursday for what we're going to get done today. Any questions about anything at all? Everything happy? Okay, great. All right, let's talk about interpolation. So we came up with two methods of doing interpolation last time, and we started a third. Now again, all of these things, if you simplify your answers, they all have to agree. Remember that if I have n plus 1 points, there's a unique polynomial of degree up to n that actually goes through all of those points, as long as I don't have repeated x values. Okay? So no matter what interpolation technique you use, if you have a quote-unquote final answer, they all have to agree. So which method you use depends on what you're doing for a computational purpose. So just to review a little bit and then get back into this third method that we were talking about. Pardon me. We talked about using a Vandermonde matrix. And remember, that was basically just a straightforward way to set up a system of linear equations based on the form of the polynomial, just the kind of a general form of a polynomial, right? So your Vandermonde matrix, you've got ones, and then you've got x's, and you've got then the x's squared, and you keep going until you get to the n minus 1 power. That's your Vandermonde matrix. Right? And then your system, I'll use a vector A to denote the coefficients that you're trying to find, is equal to those y1, y2 out to yn. That's the system that you set up. This works fine for small systems. For larger systems, it starts to get really, really bad. Our main method for solving a system like this would be to take the inverse of the matrix. It's always going to be square. It's always going to be invertible as long as you have distinct x's. So we want to take the inverse. However, the bigger this matrix gets, the closer and closer your columns get to being linearly dependent. Which if you've had linear, you know that's bad if your columns are linearly dependent. If you're taking linear, you will discover that having linearly dependent columns is bad for trying to invert a matrix. Okay? You don't want linearly dependent. And they're not ever actually linearly dependent. They're just really, really close to being linearly dependent. But from a numeric standpoint, you're going to run out of digits of precision at some point, and it's just going to treat it like it's linearly dependent, and you're not going to be able to invert it. Or it's going to be so close that your approximations to what the inverse should be are going to be way off, and so your solution will be way off. Okay. So that's the Vandermonde matrix. Really easy to set up. Really straightforward concept to set up the system. Really bad actually solving the system. Okay? That's kind of the trade, right? You see reviews of products, right? You got pros and cons. So this is kind of like pro, easy to set up. Con, going to suck for solving later on. Okay? Then we had the Lagrange polynomials. So remember we talked about those Lagrange cardinal polynomials. So if you've got x1, y1, x2, y2, out to xn, yn, are those pieces that you're trying to, or excuse me, the points that you're trying to interpolate with a polynomial. Then your Lagrange cardinal polynomial, which the notation they typically use is a script L sub I of x. The actual Lagrange cardinal is that polynomial that you use that you're going to use this particular polynomial to make sure you have the right y value at the right, try that again, the right y sub I for the given x sub I. Okay, the cardinal just means that you're actually going to use that the chunk of the polynomial, and then you'll scale it by the y. The cardinal polynomial is just, will give you 1 at that point and 0 to all the rest of them. Okay. So remember how we form that again? We do the product for I equals 1 to n, or excuse me, j equals 1 to n, but the j is not equal to I. And then you do x minus xj, and then over x sub I minus x sub j. Pardon me. Sorry. So again, this particular polynomial, if I plug in xi, notice my factors all cancel and I get 1. If I plug in xj, no matter which xj, choose any other of the x of whatever, call them i's, pick any other x of k, eventually it's going to be a 0 for one of those. So make the whole thing 0 since you're doing a product, right? Okay. So again, the idea behind this is that L sub I of x sub k, I'll use a k, is equal to 0 if k is not equal to I, and 1 if k equals I. So then your interpolating polynomial is just going to be, I'll call it P of x, will be a sum from I equals 1 to n of y sub I times the product of this thing, or times the, or what it is, L sub I of x. You use the Lagrange cardinal polynomials to generate the larger polynomial. I use the word generate. Go back to linear algebra again. Either you have seen it or will see it. The concept of a basis. Okay. If you've seen Calc 3, you use ij or physics. If you use ij and k to generate three-dimensional vectors, every vector can be written as something times I plus something times j times something times k. Ijk is what we refer to as a basis. I can write everything in terms of those three vectors as a linear combination of those three things. Okay. Basis comes up in lots of regards because you can think of lots of different things as vectors. In particular, you can think of polynomials as vectors. Okay. So when I want to generate a polynomial of degree n minus 1, I can generate that by using a 1 and x squared and x cubed up to x to the n minus 1, and then everything is a linear combination of those n things. Okay. So to generate a polynomial of degree n minus 1, I need n things to generate. In the Vandermonde case, we use what's referred to as the standard basis, 1x, x squared, x cubed, and so on. This is a different basis that we're using. The Lagrange cardinal polynomials also form a basis for polynomials of degree n minus 1. I can generate all of them by using the Lagrange cardinal polynomials. Notice that in this case, it's easy to figure out what the coefficients are by using that particular basis, right? There's nothing to solve, right? I know what linear combination to use because I'm rigging it so that I always get a 0 or a 1 at those points, and all I have to do is scale them by the constants that I need. This is my linear combination of the basis. There's no system of equations to solve, right? There's literally no, there is a system of linear equations to solve. It's the identity. It says Ix equals B, which is a really, really easy system to solve, right? I don't have to figure out what the coefficients are. They are the y values. That's the pro of using the Lagrange cardinal polynomials. There is no system of linear equations to solve. I don't have the problem of an ill-conditioned matrix. And I mentioned those words, Again, ill-conditioned just means inverting is hard for our purposes, okay? Really what it means is that if I change my inputs a little, I can change my outputs by a lot. Okay, that's what ill-conditioned means. Think about it in terms of a function, a graph of a function. If my graph is really flat, then I can change my input by a lot. It doesn't change my output by a lot, right? So that's be a well-conditioned idea. Versus if I've got a steep function, little bitty change can create a huge change. And if you think about what I was mentioning right at the beginning of class, that boundary conditions suck. A lot of times your boundary conditions can be asymptotic. And if you get close to an asymptote, you know that a really small change in input can make a really huge change in output, right? That's what ill-conditioned means in terms of matrices. Small change in your input makes a huge change to your output. Okay. We don't have that problem here for Lagrange cardinal polynomials because I know what the coefficients are. I don't have to find them. Versus in the Vandermonde matrix, I have to actually go solve and find them, right? So that's the pro of using Lagrange cardinal polynomials, is that finding the coefficients are simple. The coefficients that you're going to use are these, right? So I don't have any computational expense to finding the coefficients that I need. Where is the computational expense going to come in? Well, if I actually want to do anything with that polynomial and do evaluation, look at all the products you have to do, right? If I plug in an x value that's not one of the x sub i's, that's a crappy thing to have to compute. I've got a ton of multiplications to do, right? Okay. And they can either blow up really, really fast because the numbers are big, or they can go to 0 really, really fast because the numbers are small. Right? I also have issues with computations if your x's are not equal but are close to each other. What if they were within machine epsilon of each other? It's going to be 0 in the denominator, then I've got a problem, right? Okay, so there's your con. Pro, easy to find. Con, hard to compute. Okay. Versus for Vandermonde, your pro is easy to compute because once I find my solution, I can do my computations, and Horner's algorithm even gives you a better way to do that your major assignments on. Okay. The con is the system can suck to solve. Okay. So what we want to do, and this is what we started doing right at the end of class last time, is we kind of want to try to combine the two. Can I get something that doesn't suck so bad to solve and doesn't suck so bad to compute? Okay. And that's where that Newton form comes up. Okay. So we started talking about that last time. All right. So here's the idea again. I'm going to relabel my points to be starting at 0 and ending at n-1. Just so that the notation will match what's in your text. At least it should match what's in your text. And if you do more things in computer science, usually you start with 0 versus 1. All right. So here's the idea, and we mentioned this last time. We want to start forming our polynomials so that we can set up our system to be triangular. So again, the idea was that I want my polynomial to look like the following. I'm going to say I have a constant term, we'll call it A0, and then I'll have a coefficient on what looks like an x term, but really I'm going to subtract off the x0. And then I'll add another term where I'll subtract off the x0 and the x1. And I'll continue this until I get to the last coefficient I need. Oh, you jerk. Like so. So I'm writing this in some weird stacked form almost, right? Now, again, the idea behind this is to try to, oops, that should be an n-2, not a 2 on the end. Sorry. Again, the idea behind here is to try to mitigate most problems that we just talked about. The Lagrange cardinal polynomials had a ton of multiplications, n-1 multiplications, in fact, for every single term that you have, right? And there were n terms, right? We had n multiplications for n terms. That's a lot, right? So we're trying to mitigate that. And notice we don't, even though we have n-1 multiplications here, for each term previous to that, we reduce the number of multiplications by 1. So we don't have n minus 1 multiplications for all of them. We have n minus 1, and then an n minus 2, and an n minus 3, and so on down the line, right? We don't have n minus 1 for every single one of them, right? Okay. Now, the trade-off, of course, is that I can't get my coefficients exactly right just from looking at the data points like we could for the Lagrange polynomials, right? We've made it a little bit computationally easier, but we've increased the complexity for solving, but not to the point of the van der Waals matrix, because why? Well, I can find my A naught easily, right? Right? Because if I put n x naught everywhere that has to agree, my A naught has to be the y naught, right? Once I know my A naught, I can find my A1 by putting in x1 everywhere. X1 will kill off everything on the end except this one, but I already know what this one is, so I can solve easily. We end up with what's referred to as a triangular system to solve, which is easier. It's not nearly as badly conditioned as some of the other ones, right? So the system of equations becomes what? Let's look at this real quick. You would have your A naught has to equal your, let me write it this way. Your A naught has to equal your Y naught. Your A naught plus A1 times X1 minus X naught has to equal Y1. Because again, if I put in X1 on the right-hand side, it kills all the other terms. What does Y2 have to equal? Everything up to the X2, right? We'd have A1, A naught plus A1, X1 minus X naught plus A2 times X1, that's X2 minus X naught. X2 minus X naught, X2 minus X1. Right? Because again, when you plug in X2, you're supposed to get out Y2. It's the whole point of doing the interpolation, right? It has to go through the points. That's how we're setting up the system. Right? Just to write this off to the side, this one is f of x naught equals y naught. This is f of x1 equals y1. This is f of x2 equals y2. Right? Do you see where all the ones on the end are getting canceled out? Because every term, let's go right here. Every term past this one, there's an x minus x2 factor in there, right? Right? So all those terms will get killed. And we'll keep going. We'll get an A naught plus A1 times xn minus 1 minus x naught all the way out to A sub n minus 1 times x sub n minus 1 minus x naught. I know I'm saying a lot of words. Goes all the way out to there. Do you see why this is called a triangular system? How many variables? We're trying to solve for the A's. How many variables are we solving for in the first equation? 1. In the second equation, we have 2. Third equation, we have 3, right? If you think about writing it in matrix form, you'll have what looks like a triangle in the lower left-hand corner. You'll have you'll have a 1, and then you'll have a 1 and an x1 minus x naught. You'll have a 1 and x2 minus x naught and x2 minus x1 naught times an x2 minus an x1, right? And all these coefficients up here will be zeros, right? So on down the line. And so you get a form that looks like something that looks like this. and a bunch of zeros up here. Right? That's why this is what's actually referred to as lower triangular. Can you imagine what upper triangular is? Flip it along the diagonal. Can you imagine what diagonal is? Or what a diagonal matrix might be? Upper triangular is there's zero above the diagonal. Sorry, lower triangulars are zero above the diagonal. Upper triangulars are zero below the diagonal. Diagonal would mean what? Yeah, zeros above and below the diagonal, right? Diagonal matrix is just zero, or non-zeros are down the diagonal, right? Diagonal matrices are both upper and lower triangular at the same time. Okay. Anyway, when we have a triangular system, it's easy to solve. You can do this by a process of what's referred to as forward substitution. I can only do this by tripping over my cord. Once I know A naught, which is easy, I can figure out A1. Once I know A naught and A1, I can figure out A2. Right? And so on down the line. That's forward substitution. A lot of times when you do Gaussian elimination, which we'll talk about today as well, you do back substitution, right? Because you're putting in that upper triangular form. You figure out the last variable, you substitute in to get the second to last variable, you substitute those in to get the third to last variable, all the way up. Right? Okay. All right. Any event. This is what we're trying to do, that compromise idea. I have to solve something, but the solving is not as hard as Vandermonde. I have to compute something, but my computing is not as hard as Lagrange. Okay? It's that compromise idea. Since we're actually setting it up in this specific form, we can actually come up with a nice formula that also allows us to do this quickly, either using Excel or Python or another computer program. And that's with the method of what's referred to as divided differences. And there's going to be a nice recursive formula that's going to allow us to figure out these coefficients on our polynomial that we need based on these divided differences. So here's the idea. Okay. So, pardon me. The first thing we're going to do is that we'll define our. We're going to use brackets like this way. So we're going to define f bracket x naught really is just f of x naught. And so f of x1 is f of x1, and so on down the line. Okay, so that seems kind of dumb, right? I agree, that seems kind of dumb. But the next ones will make more sense as we go along. Let's say I have f bracket x naught minus x1. Then that difference, divided difference, is f of x1 minus, oops, I'm going to write it. Sorry, I wrote it. These need to be brackets. Okay. So your next one would be, if you had f of x1, x comma x2, that's going to be f of x2 minus f of x1, bracket x1, x2 minus x1. And it turns out that these are going to have a nice little pattern to them. This is what the recursion formula looks like. We'll see why it works here in a second. Pardon me. This one looks like f bracket x1 comma x2 minus f bracket x naught comma x1 over x2 minus x naught. I know it looks a little bit weird, doesn't it? But notice, and you keep going from this, and I'll write the next one here in a second. But notice that this is in terms of, this one with 3 is in terms of the one with 2s. The ones with 2s are in terms of the ones with 1s. That's what the recursion means. And once we get to this is the base case of recursion. If you've done recursion before, you need a base case. Otherwise, you're going to get a loop, infinite loop. Okay. You've probably done recursion before, even if you haven't done necessarily a lot of programming. If you know what this means, does it mean you scream in? No. Okay. Usually you kind of write it this way, right? Like that. But really, you can think of it recursively as that. Right? That's a recursion formula, right? So 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. 1 factorial is 1 times 0 factorial. 0 factorial is 1. That's where I stop. That's a recursion formula. So factorial is probably one of the ones you're familiar with. Fibonacci sequence does the first term is 1, the second term is 1, the next one is sum of the previous two. Okay. That's what recursion formulas are. All right, so we're just doing another one here. Okay. So if you went to the next one, if I wanted f of x1, x2, x3, well, look at the form. Notice here, when I had these three, I did those two and those two, right? So this would be f of x2, x3, x bracket x2, x3 minus f of x bracket x1, x2, and then over x3 minus x1. So notice the pattern, because we're going to write down a general pattern, and this is what's going to help us to actually create these things. Okay. Notice here, this number here is the last one. This number here is the first one. And then these just get cycled one apart. Okay. That's going to be the pattern. We'll come back to that in a minute. I want to show you where why we care. Okay. All right. So why do we care? Well, let's go back up to the system that we were just writing. We had A naught equals, write it this way, A naught equals Y naught. A naught plus A1 times X1 minus X naught equals Y1, right? What does this look like when I solve this for A1? Well, I would subtract the A naught, which is Y naught, right? And then divide, wouldn't I? So I would have A1 equals Y1 minus Y naught over X1 minus X naught. Which looks like that F bracket X1 minus F bracket X naught over X1 minus X naught. Right? Okay. Let's look at the next one. The next equation was A1 plus, or A naught plus A1 times X2 minus X naught plus A2 times X2 minus X naught times X2 minus X1 equals Y2. Well, I know what A naught is. It's Y naught. And I know what A1 is because we just found it, right? So your A2 looks like Y2 minus Y naught minus Y1 minus Y naught over X1 minus X naught times X2 minus X naught over X2 minus X naught times X2 minus X1. That doesn't look fantastic, does it? Okay. But let's see if we can get these things to connect. And I'm going to do that because I've already typed it up rather than have to write it all out. I don't expect you to copy all this down. I just want to show you where it comes from. Okay. So let me switch over to my PDF here. There. So, I don't know why Adobe's default is to want to highlight rather than just pan. Okay, do you see the top line there as what we just came up with? Okay, so this is just a lot of algebraic manipulation to get to where we need. So notice the different things I did here to get there. And yes, I literally typed this up. Okay, all right. Tried and true trick right here. Add 0, right? You've done this before. For example, if you prove the product rule in Calc 1, you add 0 in there to be able to do it. No. Yeah, product rule and quotient rule. All right. So what's another clever way to write 0? Add and subtract y1 here. Okay. And then start putting some pieces together. What did I do? Well, I just rearranged, didn't I? I put the minus y1 up here, put the minus y0 over there. And then I'm going to factor that y1 minus y0 out of the second two terms. Now that I have that, I can see it there, right? So I've got a y1 minus y0 here, a y1 minus y0 here. So I'm just factoring it out. After I factor that out, what did I do next? Got a common denominator on the inside. See it? Okay. Anything nice happen with that common denominator? I don't know why. Apparently I just copied and pasted the same thing twice. Now that I see that, that's the same line. Notice the x naughts cancel, don't they? So you just get an x1 minus x2 over x1 minus x naught. Now I just flip-flop the terms. This was on the outside, that was on the inside. Well, outside and inside. There's just it's all factors, right? So I just rearrange the factors. And then here, I have an x2 minus x1 in the denominator. I canceled it with that one. But I can't just cancel it in an individual term in the numerator, right? I have to cancel it in both terms in the numerator. I don't have it here, so I've just written it there. And now do you see your divided differences that we just talked about? Okay. So what's the moral of the story? Let's go back to what we were writing. This solution turns out to be that divided difference of, what was it? It was x1, x2 minus x0, x1 over x2 minus x naught at the very end. It was part of that recursive formula, right? So your next one, your A3, you can probably guess what it's going to be. What do you think let's do the denominator. What do you think the denominator is going to be? It'll be the x3 minus x naught. The numerator, you should get x1, x2, x3 minus f bracket of x naught, x1, x2, and so on down the line. So you can express your coefficients in terms of the Newton form of the polynomial in terms of the divided differences. Okay. I know it's a lot. What questions do you have so far? Do we see the pattern that's emerging here? Okay. All right. So this is what's going to help us to be able to figure out these coefficients from a table of values. So let's see if we can get some Excel going here. That was differential equations last hour if you weren't here. All right, so let's talk about how we actually compute this. So, let's say we want to have, let's say we have some x's and some y's. All right, let's say the x values, let's just do a few here. We have a 1, a 3/2. Again, I think I mentioned this last time, but anytime you want to type division, make sure you put an equal sign in there. Otherwise, Excel is most likely going to treat it as a date. Okay. All right. Excel's like the creepy dude that treats every interaction like a date. Anyway. 3, 13 over 4, 3, and 5 over 3. All right, so the x values were 1, 3/2, 0, and 2. The y values were 3, 13/4, 3, and 5/3. Okay. So basically what we're going to create here is going to look like a triangle. I'm going to do these different quotients so that I get those different divided differences pieces. Okay? So what I'm hoping at the end is that this top row here is going to give me the coefficients that I need. Okay? I already know that this is the correct, if I start at 1, then this is going to be the correct constant that we need, right? Now, you might have different forms depending on the different order of your points, by the way. If I reorder these points in a different way, I'll get a different looking table, but I have to end up with the same polynomial when I'm done. Does that make sense? Okay. All right, so let's talk about how we do these. The first thing we're going to do is I'm going to compute the divided difference for these three. Okay. So let's see how that works. So for this one, I want to do the next y value minus the previous y value, and then divide by the x's that correspond. This one and that one. That was the formula that we came up with for the second coefficient, right? We agree? Okay. So literally just putting that in, I'm going to copy that down just to the next two. I could copy it down to this one, but I could copy it here, but notice that we don't have any y value here, right? So copying this down doesn't mean anything for us. So we're always going to copy it down to one spot less, right? Okay, so let's think about why the next formula is the way it is, all right? What was our next coefficient? Our next coefficient, I'll write it down off to the side here, was the divided difference for x1, x2, minus, or sorry, the f bracket of x1, x2, minus f bracket of x0, x1, over x2 minus x0, right? That was our next formula. This number, that is that, right? And then likewise, the one above it is this one. Okay? So for the next one here, let's see if I can Erase that. So this next one here is going to be what? We'll do this one. Oops, I need parentheses. This one. That's the f bracket x1 comma x2. Right? Comma, oh, sorry, not comma, minus this one. What are we going to divide by? Yeah, the 0 minus the 1, right? It's this farther apart. So we'll do this one minus this one. Does that make sense? Okay. Enter. I'm going to copy that down one spot. I'm going to come back to these other values in a minute here, by the way. Now, our A3 should be f bracket of x1, x2, x3 minus f bracket of x0, x1, x2 over x3 minus x0. Notice the two values that we just came up with are these two things, right? Okay. So here we'll do this one minus this one, D3 minus D2, and then divide by which two x values? Yeah, A5 and A2. Good. The outermost ones. And that's when you know you're done, right? Because I'm getting to those last x values that I have. And so I get a -2. Okay. So let's talk about what the answer is. Let's do a little bit of graphing, and then I'm going to come back to the rest of the points in the spread the table that we have and talk about those just for a minute. This okay? Getting it set up? All right. So our polynomial, our f of x, these are our coefficients. So a 3, a half, as I can tell that's 0.5, a 1/3, and a -2 are the coefficients, right? The 3 doesn't get multiplied by anything, so I don't know why I left a big old space there. The 1/2 gets multiplied by x minus what? What x value should we subtract off the x? Yeah, the x naught, the 1, right? The first x value that we have. What gets multiplied here by the 1/3? You should have an x minus and an x minus. Should be two factors here. What goes there? We didn't subtract any x's off the first term. We subtracted the first x off the second term. So what goes off the third term? I'll say it again. We didn't subtract any x's off the first term. We subtracted the first x off the second term. So which x's are we going to subtract off the third term? The first and second. Good. 1 and 3/2. What's going to be the last on the last term then? How many factors are we going to have here? 3. X minus 1. X minus 3/2 and x minus, oops. The last one's going to be x minus 0. Good. There's your polynomial. On. I'm going to do this. I'm going to graph this in Desmos to make sure that we actually went through all 4 points. But let me ask you, if I would have asked for the Lagrange form, what would this look like? This was Newton. It was what we just found. What if I asked you for Lagrange? Let me ask you first. What would the coefficients be on your Lagrange cardinals? That should be the easy part. What are the coefficients that you would use for each of your Lagrange cardinal polynomials? The y values, right? So the first one, you should have a 3. Oops. F of x should be 3 times something, and was 13/4 times something, and 3 times something, and what was that? 5/3 times something. Times what? How many factors should you see in the numerator and in the... Start again. We have 4 points. Given the fact that we have 4 points, how many factors should we see in the numerator and in the denominator for each of your cardinal polynomials? 3, right? There's always one less factor than there is point, right? Okay. If I'm using the y value associated with 1, what should be the 3 factors in the numerator? Good. So this was 3 halves, 0, 2. This was 3, 13/4, 3, and 5/3. So yeah, you should have an x minus 1. I have to move this over a little bit, it looks like. An x minus 1, and or not 1, an x minus 3 halves, an x minus 0, and an x minus 2, right? What does the denominator look like? Fantastic. That's exactly right. How about the second one? Numerator is going to look like 3 factors. They're all going to have the form x minus something. What are we going to subtract off? Good. Yeah, you leave out the one that you're working on, right? We're working at 3 halves. We leave out the 3 halves in the top, right? The denominator looks like the numerator. You're just going to replace the x with 3 halves, the x value that you're working on. So we have 3 halves minus 1, 3 halves minus 0, 3 halves minus 2. What's the next one?
X minus 1, x minus 3 halves, x minus 2.
Good. And then we'll have 0 minus 1, 0 minus 3 halves, 0 minus 2. And the last one, 2 times, I'll just write it out, x minus 1, x minus 3 halves, x minus 0, 2 minus 1, 2 minus 3 halves, 2 minus 0. 5/3. Sorry, my value there. I put the x. Are we okay with where we got both of those? If not, this is the time to ask. Yeah? Okay. Let me plot these points. on Desmos and show that both forms, I'm going to type in both forms of the polynomial and show that they both go through those 4 points. Okay? So the first point was 1, 3. Second point was 3 halves, 13 fourths. The next one was 0, 3. And the last one was 2 and 5/3. There they are. So I can see the 4 points there, right? I hope I can see the 4 points. All right. Our first polynomial, the Newton form, was 3 plus 1/3 times x minus 1 plus 1/2. I wrote a 1. Oh, I got them back. Oh, no, sorry. It was a 1/2. I got that backwards. It's 1/2 times x minus 1. 1/3 times x minus 1 times, stupid big fingers, 3 halves. And then minus 2 times x minus 1 times x minus 3 halves times x. Hey, look at that. I went through the points. That's good news. We did it right. How do I know I did it right and not I think I did it right? How do I know I 100% did it right? How many points do we have? 4. What should it be, the degree of the interpolating polynomial? Third degree. Does that look like a third degree? Absolutely. How many degree free polynomials go through those points? 1. That is the right answer, right? I know that it is correct. Not that I suspect that it's correct. I know it's right. I typed in a third degree polynomial without a doubt, right? Each of those, especially the last one, is cubic, right? I 100% typed in a third degree polynomial and it 100% went through the 4 points. It's 100% correct. I have no doubt. That's good. You don't get that very often, right? Usually you do the graph things like, well, I think I might be right. No, I know I'm right. Damn it. Okay? Right? Okay. Now, again, we said there's exactly one polynomial that goes through those points, right? So let's type in the other form that we just found. We had, the first one was 3 times x minus 3.1 1/2. I'm going to type 1.5 just so I don't have to type the 3 halves every time. And an x minus 2. And then I have to divide by, it was 1 minus 1 minus 3 halves, 1 minus 0, 1 minus 2. It should give me a positive 1/2, it looks like. It was negative 1/2 times 1 times negative 1. Yeah? So instead of dividing by 1/2, I could just multiply by 2 for the first one. Notice already I have a cubic, right? So we're going to be modifying that cubic with other cubics. Okay? The next one was 13 over 4, and then times x minus 1 times x minus 2. The denominator was 1/2 times 3 halves times negative 1/2. Negative 1/4 times 3 halves is negative 3/8. I did that right. So I should have an 8/3. We'll know if my arithmetic is right because, again, it should match the other polynomial when I'm done. Okay. Then I got a plus 3 times x minus 1 times x minus 3 halves times x minus 2 divided by, negative 1 minus 3 halves minus 2. So I get 2 times negative 3 halves is a negative 3 that we're dividing by. And then finally, plus 5/3 times x minus 1 times x minus 3 halves times x divided by 1 times 2 is 2 times a half is 1. So I shouldn't have to multiply by anything, which I can see because it's on top of the other graph if I would have just looked. So we really do get the same answer, even though they're very different looking forms. Neither of which are in our kind of our standard form, right? Questions on that? We'll do another divided difference one here in a second. But are we okay with how we got these? Just stunned amazement. Yeah? Wow! All right. I did want to mention again, like I said, I want to go back to this table, and then we'll set up another divided differences table for just a slightly larger polynomial. So, let me flip back over. All right. That was what we came up with our table, all right? Let me go and just ignore the first row. Do you think you can tell me what the coefficients are for the polynomial that passes through those 3 points? I bet I can. I bet it's the top row. I can now find the quadratic through those 3 points without doing any extra work. Those coefficients are the correct divided differences for the quadratic that goes through 1.5, 3.25, 0, 3, and 2, and 2, 5/3. Okay. I can also find the coefficients for the line that goes through those 2 points in the same fashion. So those other points that are in your table, not only are we using them to figure out our final answers, they also give us some intermediate interpolating polynomial coefficients as well. All right, let's do another one with some more points here and see if we can get it set up correctly. So let's say let's do doesn't really matter. Let's see if we do a little slightly bigger. Let's say I have x and y, and we have 0, 1, 2, 4, 6 for the inputs, and 1, 9, 23, 93, and 259 for the outputs. You might be able to just use the table you typed and modify it. Work on it for a minute, and then we'll chat. See if you can do it. Is it a what? 93, yep. It's an arrow 3, it looks like. Ready to chat about it? So we got about 5 minutes. Does it look like that? Yeah. Let me show you a quick, well, maybe quick. So here were your original divided differences. I didn't actually do it here, but let me show you what you could do. If you wanted to be kind of fast about it, you could go over here. I don't ever want, as I copy to the right, I don't ever want to change the left column. So I can use an absolute cell reference to help me. If I hit F4, remember F4 will put dollar signs on both of them. I want the row to change, but not the column. If I hit it again, it puts just a dollar sign on the row, which I do want to change. So I flip it, and now my dollar sign will hold my A hold my A as I copy to the right. And I can do the same thing for the second one here. As a matter of fact, I can just type a dollar sign in there. I can copy this down to get those. The only reason why that can help me is if I do this now and move over, this isn't quite right, but it's close. What do I need to change? I need to change this 2 to a 3, right? And then I can copy that down, and I don't have to type nearly as much stuff. If I use that absolute cell reference, I can copy to the right and just edit one cell and then pull it down and do it across the rest of them. It's just a little bit quicker. Okay. Anyway, is that what you got? What does this 0 tell you on the end? That would be our coefficient on that highest degree term, right? We have 5 points. We know it's an interpolating polynomial of at most degree 4, right? But what, do I need a degree 4? No, I can do a degree 3, right? And in fact, you got lots of different options for coefficients, but I would probably just use these then for my coefficients. Because I could just eliminate this point and just use that table as the one I need. And then you can check that you really do go through the 0.01. When I get to this 0 here, it tells me I don't need that point, right? I don't need that point, so I just ignore it. I'm going to use those instead. So let's see if that actually works. I'll write it on the board since I'm on the computer rather than and of course I'm recording dead air on the other computer right now. That's okay. What would the form of the polynomial be? If I just use those last points, what would my polynomial look like? Careful, not 1. 9, right? Because it's the y value, right? But you're on the right line. Good. The next coefficient will be 14 times. Good. X minus 1. Okay. And finally,
X minus 1, X minus 2.
good. All right. So that would be our polynomial, right? 9 plus 14 times x minus 1, and then the rest. Let's see if that really does go through the points correctly. Let me kill all of these things. We got about 2 minutes. Let's see if I can get this typed in 2 minutes. All right, the points that we had to start with were 0, 1, and 1, 9. I wonder if I can type multiple points in here at the same time. Nope, sure can't. Well, maybe it did. Oh, yeah, it did. Okay, well, that's cool. 4, 93, and 6, 259. And the equation was 9, or the function was 9 plus 14 times x minus 1 plus 7 times x minus 1 times x minus 2 plus x minus 1 times x minus 2 times x minus 4. And And it really did go through all the points. Okay. So we really did make it through there. And we also confirmed there that it goes through the 0.01 as well. It was the one we left out. Okay. Is this okay? Would you say that this polynomial does a good job fitting those points? Yeah, so you could probably use it to approximate things in the middle, which is kind of the point, right? If I have some data, I'm probably trying to find a polynomial that goes through it, right? To see if I can use that to fit some, use that to interpolate, right? Find some intermediate values for that. That's the point. All right. We will chat about that in the idea of being able to, of whether or not the approximation is good. We'll talk a little bit about that on Tuesday, and then also talk about do some solving of systems of equations on Tuesday. So have a good one. We'll see you Tuesday. Thursday. This is Tuesday. Whatever day it is. Have a good one, everybody. Yeah.
Is that what Excel does?
What's that?
Is that what Excel does? You do a polynomial like data?
I think polynomial fit does polynomial regression rather than interpolation. Yeah, I do not think that it does that. I don't know that 100% certain, but I think polynomial fit, or polynomial does a polynomial fit to the data as a regression. So it's trying to minimize the error.
Okay.
Yeah.
So you know how we had the 0 on the x to the fourth
Yes.
power term?
Yes.
Could you use that polynomial?
Yeah, that should work. Yeah.
It'd be the same thing.
It should be the same thing. And you should be able to test to make sure that it is the same thing. Yep. Yeah. I just think it's a little bit easier to recognize that, oh, that came out to be a 0. I don't need that point.
Yeah.
So I just throw it out and I'll use the other one.
Yeah.
Yep.
Sounds good.
Yep.
Thank you.
You're welcome.